Assalamualaikum and hi everyone. So welcome back to the second part video of calorimeter. Okay, so in my first video of calorimeter, we already done 5 different calculations involving simple calorimeter where heat release is only equals to heat absorbed, and the heat release comes from other substance and heat being absorbed by water. Okay, so in this part 2 video, we're going to deal with a more difficult questions where we are evolving calorimeter into our calculation. Okay, just to recap, there are 2 types of calorimeter, which is the first one is your simple calorimeter and the second one is your bomb calorimeter. Okay, so if a simple calorimeter, most of the times we have negligible heat capacity. So negligible heat capacity means we don't include the heat capacity into the calculation. Okay, whereas in the bomb calorimeter we have to include the heat capacity. Okay, so in these two will give you to a different formula to calculate how much heat is being transferred between heat release and heat absorbed. Okay, let's do one by one. Okay, so for simple calorimeter which has negligible heat capacity, so Q release is simply equals to Q absorbed. Okay, which is mostly our Q absorbed is the Q of your water. Okay, so let's continue here. So Q substance equals to Q water. Okay, or other substance that is present. Okay, whereas for the bomb calorimeter, since we must include the heat capacity of the calorimeter, so it's now become Q of the reaction, or this reaction can referring to any substance, okay, equals to Q water plus Q calorimeter. Okay, if in this one, if water is present, okay, so if water is present in the calorimeter, okay, but sometimes we might not have water in our calorimeter setup, so the equation will become Q reaction equals to Q calorimeter. Okay, if no water. Okay, so your Q calorimeter, okay, it depends, either they give you heat capacity or specific heat capacity, but mostly for calorimeter they will only give you heat capacity. Okay, so Q calorimeter is equivalent to C stand for heat capacity of calorimeter times with the delta TC. Okay, so this is heat capacity, and the unit for heat capacity is joule per Celsius. Okay, right, so just to label this equation, if no water is present in the calorimeter. Okay, so you have to remember that one. Okay, so if they give you heat capacity, so that means it's just heat capacity multiplied with the change in temperature. But if they give you specific heat capacity, so small c, so Q equals to mass time with the specific heat capacity time with the delta T. Okay, so this C referring to specific heat capacity, which this specific heat capacity has the unit of joule per gram per Celsius. Okay, so you have to be alert what kind of information is given to you. Okay, so let's try now answering the questions that I give to you for your second hour tutorial 3rd week. This is the first question where you were given, okay, combustions of naphthalene. Okay, so let's highlight what is the substance being used. So we have naphthalene here, can be used to calibrate the capacity of a bomb calorimeter. Pardon me with the typo, so this one should be of a bomb calorimeter. So the heat of combustion, okay, so they give you heat of combustion. Heat of combustion here is referring to enthalpy of combustion. Okay, so When 0.8210 gram of naphthalene was combusted in a calorimeter containing 100 gram of water, a temperature rise of 4.21 degrees Celsius was observed. So determine the heat capacity of the bomb calorimeter. So our question here is to find out what is the heat capacity of the bomb calorimeter. So heat capacity is big C, capital C. Okay, so they give you this is the mass of your naphthalene. So naphthalene. Okay, so this one is the temperature change. Okay, and in this one, since it has water in the calorimeter, so your Q release, okay, Q release equals to Q absorb, and in our case we have Q release is from the reaction of the combustion process, okay, and then is Q water because water is present in our calorimeter plus Q calorimeter. Okay, so how are we going to calculate our Q reaction? Is by using the enthalpy of combustion given here. So first step, okay, calculate number of mole of our naphthalene. Okay, so N equals to 0.8210 gram divided by the molar mass of naphthalene is 12 times 10 plus 8 times 1 gram per mole. So that's how you're going to calculate the number of mole. The number of mole of your naphthalene that is present, okay, is 6.41 times 10 minus 3 mole. Okay, so step 2, okay, you're going to calculate the Q reaction by using the enthalpy of combustion given. So how do we get enthalpy of combustion? Okay, so enthalpy of combustion is equals to Q reaction over number of mole. Okay, so we have here enthalpy of combustion is 5132.8 kilojoule per mole. So that kilo I need to change it to scientific notation because it must be in joule. Okay, joule per mole equals to Q reaction over number of mole is what we already calculated before, which is 6.41 times 10 minus 3 mole. Okay, what should we do next? We're going to multiply the enthalpy of combustion with the number of mole to get our Q reaction. So we get our Q reaction to be 32901.2 joule. Okay, so now we already have our Q reaction. Okay, so we can proceed to solve our C calorimeter. Is 32901.2 joules. Okay, so equals to heat absorbed by the water, which is MWCW delta TW plus Q calorimeter is C cal times with delta T calorimeter. Okay, so the temperature change for both water and calorimeter should be the same because they are present in the same vessel, okay, in the same container. So they must have the same temperature changes. Okay. Okay, so for the temperature change should be equivalent between the water and the calorimeter because both of the calorimeter and water is in the same place, in the same container. Okay, so that's why they undergo the same temperature change. Okay, so now let's solve for the heat absorbed by the water. Let's calculate for that one first. Okay, and then I'm going to move, okay, the value of heat absorbed by water to my left side, so it becomes subtract, okay, or minus in a simpler words. Okay, so from there, I'm going to calculate what is my C calorimeter by dividing the heat of the calorimeter, okay, with 4.21, which is the temperature change, to get my C cal. Okay, so this one turn to this one, it becomes division. And from there, I'm getting my C calorimeter to be 7397. Okay, joule per Celsius. So let's rewrite. So the answer, C calorimeter is equals to 7397 joule per Celsius. Okay, please don't get confused. Okay, the unit for the heat capacity is joule per Celsius, because heat capacity is the amount of heat needed to raise the temperature of the substance by 1 degree Celsius, whereas, okay, for specific heat capacity, okay, as shown in the specific heat capacity of the water, okay, so that is the amount of heat needed to raise 1 gram of the substance by 1 degree Celsius. That's why it has gram in the unit, okay, per gram in the unit. So let's move on to the second question. Okay, so let's look at it. Okay, so we have here 0.1326 gram of aluminium completely combusted in a constant volume bomb calorimeter with heat capacity of 1410 joule per Celsius. Okay, so we have two types of calorimeter. One is constant pressure calorimeter. That one is referring to your simple calorimeter. If it's constant volume calorimeter, that one is referring to your bomb calorimeter. So everything here is already included in your notes, so please check on it. Okay, so the bomb calorimeter was surrounded by 800 gram of water. Again, in this calorimeter, there is water present, so heat absorbed is applied for both water and the calorimeter. Okay, so the temperature of the bomb and water increased by 1.726 degrees Celsius. So calculate the heat of combustion of aluminium. So this one, they want you to calculate what is the enthalpy of combustion of the aluminium. Okay, so there are 3 steps again. Okay, for the second part of calorimeter, it always involves 3 steps. Okay, it just you need to rearrange which one comes first. Okay, so the step 1 is for you to calculate Q reaction. Okay, Q reaction equals to Q water plus Q calorimeter. Which this comes from the concept of heat release, okay, equals to heat absorbed. Okay, so the Q reaction is referring to the heat of the combustions of aluminium. Okay, so QW is MWCW times with delta T plus C calorimeter times with delta T. Okay, so mass of the water is 800 gram times with 4.18 times with the temperature change, which is 1.726 plus, okay, so our heat capacity of the calorimeter is 1.1410 joule per Celsius times with the temperature change is 1.726. So we get here our Q reaction is equals to 8205.40 joules. So we need to convert it into kilojoule, which divide by 1000. Okay, 1, 2, 3. So my Q reaction becomes 8.205 kilojoules. Okay, so secondly, okay, we need to calculate what is the number of mole of the aluminium used. Okay, so mass divided by the molar mass, which is 27 gram per mole. Okay, so you will get the number of mole to be 0.00491 mole. Okay, so the third step, after you obtain what is the Q reaction, okay, and what is the number of mole, so we need to calculate enthalpy of combustion. Okay, so enthalpy of combustion is the heat release when 1 mole of substance is completely combusted in oxygen at standard condition of 298 K and 1 atm. So it is heat release, so that means it become negative Q reaction divided by number of mole of our Al. So delta H combust equals to, okay, so Q reaction is negative 8.205 kilojoules. Okay, so divide by the number of mole of our aluminium, which is 0.00491 mole. So it leaves you the answer to be negative 1670.7 kilojoule per mole. Okay, so whenever you need to calculate the enthalpy of anything, enthalpy of combustion, hydration, or atomization, or so on, you need to be alert. Okay, the final answer should include the sign. If it is heat release, just like in your enthalpy of combustion, then this minus sign should be included in front of your answer, or else you will not be given for the final marks, even though you get the correct value of the enthalpy of combustion, but without the negative sign is completely wrong. Okay, so let's discuss with the third question. Okay, this time you are using a metal hydrazine. Okay, let's highlight. Metal hydrazine has this formula, okay, which is being used in a liquid rocket fuel. Okay, the combustion of metal hydrazine with oxygen produce nitrogen gas, carbon dioxide gas, and water. Okay, so these are the products. Okay, so when 4 gram of methyl hydrazine is combusted in a bomb calorimeter. Okay, so when it says that bomb calorimeter, so that means C calorimeter is included. So C cal is present. Okay. Okay, the temperature of the calorimeter increases from 25 degrees Celsius to 39.50 degrees Celsius. Okay, the heat capacity of the calorimeter is measured to be 7.794 kilojoule per Celsius. Calculate the heat of combustion. So question asks you to calculate the heat of combustion. Okay, in my first 2 examples, water is present in your calorimeter and they tells you the information about water in the question statement. But in this question number 3, can't you see any water is being given, any information about water is being given, either the mass or the temperature rise or anything related with your water? Nothing. So that means in this example 3, there is no water is present in your calorimeter. So heat released by the reaction is equals to the amount of heat absorbed by the calorimeter. So simple this one. So heat release equals to heat absorbed. Okay, so write down here first, so for you to remember, no water is present. Okay, so it becomes Q reaction equals to Q calorimeter. Okay, so first step. Okay, so this one. Okay, so to revise in the second example before. Okay, so you have 3 steps. Okay, whenever you need to solve this kind of problem. Okay, so first step you need to calculate Q reaction. Second step to calculate the number of mole, and third step is to calculate the enthalpy. Okay, but in this time we need to calculate the enthalpy, so you must follow this step. So first start with calculating Q reaction. So Q reaction equals to C calorimeter times the temperature change. Okay, so C calorimeter is 7.794. Okay, please take note this one is in kilojoule. Okay, so that means you need to make sure the final value of your Q reaction is in kilojoule. Okay, so the temperature change is from 39.50 minus 25 degrees Celsius. Okay, so your Q reaction should be 113.1 and it is kilojoules. Okay, so step 2. Okay, so in order to calculate heat of combustion or enthalpy of combustion, you need to know first what is the number of mole of my hydrazine here. So methyl hydrazine. Okay, so number of mole is simply mass of the methyl hydrazine used, which is 4 gram, divided by the molar mass. So we have 1 carbon, so 12 plus 6 hydrogen plus 2, and your nitrogen is 14. Okay, the unit is gram per mole. The number of mole of your methyl hydrazine used in this experiment is 0.087 mole. Okay, so final step is to calculate what is the enthalpy of combustion. Okay, so enthalpy of combustion is a heat release, no negative reaction. So negative Q reaction over number of mole of our methyl hydrazine. So negative 113.1 kilojoule divided by 0.087 mole. So your enthalpy of combustion is equals to negative 1300 kilojoule per mole. Okay, so that is the final answer. Okay, so let's move to our fourth questions. Okay, so you're given 0.5865 gram sample of lactic acid. So this is the molecular formula of your lactic acid, which is burned in a calorimeter with heat capacity of 4.812 kilojoule per Celsius. So the temperature increases from 23.10 to 24.95 degrees Celsius. So calculate heat of combustion of your lactic acid. Okay, so in this fourth example, it's exactly the same like your in the question number 3, which you only have calorimeter without any water present inside it. So no water present. Okay, so the Q reaction is equals to Q of the calorimeter. Okay, so that is your first step. Okay, to calculate what is the Q reaction. Okay, so Q calorimeter is equal to C calorimeter times with the delta T. So your heat capacity of the calorimeter given to you is 4.812, and please take note it is in kilojoule per Celsius multiplied with the temperature change. Okay, so 24.95 minus 23.10 degrees Celsius. Okay, the Q reaction for this one is 8.90 kilojoules. Okay, so let's move on to the step number 2. We need to calculate the number of mole of our lactic acid. Okay, because we want to calculate what is enthalpy of combustion. So to get enthalpy of combustion, you need to first calculate the number of mole. Okay, so number of mole is mass of the lactic acid, okay, divided by the molar mass. So we have here 6 hydrogen plus with 3 carbon, okay, plus with 3 oxygen. Number of mole of your lactic acid is 6.52 times with 10 to the power of negative 3 mole. Okay, so let's move on to the final step, which is to calculate what is the enthalpy of combustion. Okay, so the formula is it's the heat release, so negative Q reaction over N lactic acid. Okay, so our Q reaction is 8.90 kilojoule. Okay, please take note about the unit is now in kilojoule instead of joule, divided by the number of mole, which is in mole. Okay, so let's calculate what is the enthalpy of combustion of your lactic acid. Enthalpy of combustion of your lactic acid is 1365 kilojoule per mole. Okay, as you can see, we already done 4 different questions. It always involves these 3 different steps, okay, by either starting with calculating Q reaction, and then number of moles, and lastly enthalpy of combustion. And sometimes you might need to go in a reverse direction, okay, by using the enthalpy of combustion, okay, to get the Q reaction. Okay, and maybe if the question asks you to calculate what is the heat capacity of the calorimeter or what is the temperature, change. So I'm going to give you a more difficult questions to test on your calorimeter understanding later on for your third hour tutorials. Okay guys, so we are done with the second hour's tutorial for this week. I'll see you guys again in my third video. Bye bye.